Welcome everybody. All right, go in, please. We're just about to start this edition of the Deep Seminar. It's a pleasure to have Alex Rene here, all the way from Aachen, and he will tell to us about truth in the age of deep learning.
Yeah.
Building a model selection criterion which survive replication.
Right. Okay. All right. Yeah, I like talks because I can make titles more punchy than what I can do in papers. So yeah, let's see if I can live up to this hype. Yeah, so basically let's get started. Maybe I just what is this volume thing? Or is that always gonna stay there? Oh no, okay. Oh, I should not move my mouse. That's a bit, let me move the mouse off of the screen then. All right. Yeah, just to give an idea of where I'm from, right? So like Wout mentioned, I'm in Aachen, so I'm in the computational network science group there from Michael Schaub. This particular work was funded by mostly a BMBF grant from where I was before with Mauritania, also at the FETH, but also like some of the final steps I did under this ERC grant that I'm currently paid from. Just to, so I'm going to leave this on for like a minute or so. So if you want to follow along, these are a few links you can use. So if you want to click through the slides, you can go to here. So if you want to look back on slides that you missed, you can use that. Otherwise, you know, the paper of what I'm going to talk about is there. Obviously, you can just find it on my website. I'll have the link to my website at the end. And I have a few pictures there just to kind of give a flavor of what we're going to talk about. These are pictures, right? So they're not really what we're going to do graphs, or we're going to do figures, but I thought pictures were more fun to look at. So basically, we're going to look at two different kind of example models to test this idea of model selection. One is going to be the circuit of the lobster caloric rhythm. So lobster, I mean, this is just a useful system to study because the ethics approvals for lobsters are not too difficult to get. So you can do experiments with them fairly easily. So it's been a model system for kind of complex dynamics in neurons of like small circuits. And basically I'm using a model from that. And then I'm also going to be using as a kind of very toy example some standard models for black body radiation, which is why you have a picture of a star. All right, so we can get started already. Before I kind of talk about what kind of the method I'm going to talk about, it's, I think, important to have a clear idea of what we want to solve. Like, what is the problem that we're trying to solve? So you can think, like, what is it, if you're in a very kind of, I don't know, popular science way, like, what does a scientific process look like? I mean, you basically would start from anecdotal observation. So, you know, you see something in nature, you're like, oh, this looks pretty cool. I want to understand that this happens. I want to turn this into a model that I can then, you know, put equations on, study the parameters, see what happens. Like, what are the key interactions that help me understand this phenomenon? So you start from anecdotal evidence, and then you kind of build your model from this. So the first step would be to identify some kinds of symmetries, or, you know, what kind of conservation laws you have, or you know, your assumptions, like this is about thinking, looking at what you saw. In this case, you know, clearly rotational symmetry should somehow be involved. Whatever, I mean, that's your kind of modeling step. And then you conceive a theory. You would probably do some experiments if you're not a complete theorist. And then you make some predictions, you accumulate some data, and then you come back and you validate your theory. That's basically, that would be kind of very high level, you know, loop of the scientific process. So we want to, basically, we're going to be talking about this thing here. And then if you know, at that point, you would probably do some new experiment. All right. So why do I bring this up? Because, I mean, this kind of diagram is going to sketch out what the requirements for our model selection process is going to be, right? So you could imagine having multiple theories that you want to see which one fits better to the data, which maybe, you know, which of these conservation laws you need to preserve, whatever. And then, you know, what is it that we need as a requirement focus? So the first thing is that what we want to do is induction, right? So what we don't want is to describe specifically only the model that is or specifically the data that we recorded. We're not super interested in this pack of flies. Right? We want some model for how packs of flies behave in general that we can go out and see new observations and still make useful predictions on that. So that's a concept, that's induction. We are most interested in predictive accuracy. Well, that's going to be kind of our measure of success. If you're able to predict accurately what's going to happen, this is how we measure. And that, I mean, that's standard kind of scientific practice as well, right? How do we test physical theories? We make predictions, and then we go out and we see, you know, that the transit of Mercury happens at the time that we expected it to happen, and then we call that a success. The other thing that should be obvious for this kind of setup is that no model is perfect, right? So we are not in the realm of, you know, general relativity where we can get things down to like 18 significant digits. We are happy if we get 2 significant digits for these kind of biomodels. So definitely no model is perfect. That's not necessarily a bad thing, right? So we often would like something that's somewhat simpler than the complete full complex dynamics, especially if you're talking about emergent phenomena. We want to factor out, you know, the small details, figure out, focus on the macroscopic, and so a key feature is that no model is perfect. And the other thing is that we don't have like a set amount of data, right? So if we do some recordings, we get some data, we test our theory, we're like, it seems, you know, we get like 2 sigma significance. We'd like to push this up. We go out and get more data. We'd like to kind of augment the data. So that's, you know, kind of standard for all these should sound familiar, I think, if you're like a physicist or someone doing standard science. But all of these requirements are also kind of at odds with the standard tools you'll find in statistical methods for model selection. So typically they don't do induction, they do description. Predictive accuracy might be used in some sense, or they might tweak it, but usually it is assumed that the model is in, your true model is in the data set. So that's another thing that's different. And for sure, the criterion that you get out of statistics are not robust to changing the amount of data. So if you go back and you collect more data, you can't apply the criterion anymore. Like the whole framework of that criterion is invalid. All right. So that's I put it up at the front because it's important to well circumscribe what is it what we want to do and what is it that we don't.
Can I ask a question?
Yes.
You mentioned predictive accuracy.
Yes.
Do you have in mind that the objective to make point predictions and they should be accurate, or is it more?
It doesn't really matter. It's like whatever you want to predict is your measure.
Something more predictable uncertainty. So it's also important to get it.
I mean that is
of how certain you are about your prediction, right?
So that I mean essentially those two things are, I mean, I see them as two sides of the same coin, right? So how do I measure predictive accuracy? I measure the amount of inaccuracy. So I'm going to have some loss function that tells me for any prediction how wrong it is.
Well, it wouldn't also be to have an accurate prediction of your uncertainty bounds, right?
Oh, I see. Whether you want to get accurate predict. Okay.
So that once you make a new prediction,
yeah,
you have, well, you can say something about how.
Yeah, I think, I mean, in a way, that's kind of just another level up of modeling, right? So if I'm trying to predict the movement of individuals, that's, you know, and then I assess whether that is accurate or not by some metric of distance. And then if rather my prediction is I'm trying to predict the uncertainty of that first model's prediction, you can all fit this into the same framework, I think, but it's just one level up of model. It's like a model of the model or a model of the uncertainty of the model. But I'm not going to go into that route. We're going to stick with, basically, I'm going to assume that we have some function of the loss that tells me what is the cost of making a mistake. If I make a mistake, if I make a prediction, I make an observation, I'm going to have some difference between the two because the model is not perfect. and then I have some function that returns a real number that says this is how wrong you were. And essentially you want to yeah.
That was more geared towards point.
Yeah, I guess. But I mean it's any functional of your prediction will work. Anything that returns a real number will be fine. So it's in this sense it's generic, but I think it's easier to think about point prediction if you but I don't see a reason why it cannot be generalized. Okay. To kind of what we're going to work with is basically two toy models. I mean, as much as I would like to work with data, I always end up doing theory somehow. So we're only going to be using simulated data, but it's fine. It's sufficient for what we want to do. So basically, we have one very toy model, which is essentially inspired by the ultraviolet catastrophe. So you have the radiance of a black body. I mean, I think most people here are physicists, so you should be familiar with what this does. So it's essentially if you are in a particular regime of the wavelengths of the particular spectrum of electromagnetic, then the emission, like the radiance of a black body, is well described by either of these two models. All right, this is like the classical model. This is the quantum model of Planck from the turn of the 20th century. And so, I mean, in this particular case, if you go into basically the visible range or lower wavelengths, or larger wavelengths, sorry, you essentially see the curves are more or less the same. And if you simulate some noise in your photodetector, you would say in this case, for example, that it's hard to say which. That's kind of the idea, is that we're in a regime here where we don't know which one is better. I'll show a plot later where you would totally know which one is better. And that's kind of the idea. We can control the amount of confusion between the two candidates that we're trying to compare. And that's kind of a useful axis to have when you're trying to design a model selection criteria. But this is very pedagogical. It's useful because I have like nice one-dimensional axes that control the kind of things I want to control. But it's not very close to the kind of thing you would want to do, right? So something that's closer to like a realistic scenario and closer to where I was coming from when I devised this method is something like on the right. So so this is the crustacean polaric surrogate that I alluded to earlier. If you're not familiar with the kind of conductance model neuron equations, that's completely fine. You don't need to be. Just understand that this is a complex dynamical system with a lot of interacting parts, and this M and this H are themselves functionals of V. So the whole thing is very, like, the interactions are quite complex, right? So it's not just, I mean, it looks like some linear model here, but that's because all of the nonlinearity is kind of hidden into this M and this H, which have their own functions, which have to be just fitted to data because there's no theory for this. So that's your dynamics. And then what happens, if you plug this into a small circuit, so in this case, I took 2 neurons from, so these are like published data that people have been using for a while. So you can get, the model actually goes back to a little bit before the 2000s, but this is maybe the one that puts everything together. And that was, is the reference for this. And then I also have like my implementation that I collected. So if you're looking for, all the parameters, it's maybe a bit easier to get my implementations when I get. Otherwise, you have to look through 4 different publications to get all the numbers. Anyway, but if you plug this together, you can get simulation. You can get data like this. So you basically have this driving neuron that has like a spontaneous activity where it'll fire a bunch of bursts for a while, and then it kind of gets tired, and then it falls back down. And then this repeats again. So you have these kind of slow calcium dynamics that slowly change how easily it is for calcium to go across the membrane, and that's what drives these kind of switches between these two states. And then this is what they call a kind of pacemaker neuron. So it just spontaneously does something like this, and then this drives some response in some kind of downstream neuron that will react in some way. And the way we're going to set the problem is that we ask, okay, I record this, and I would like to have a model of this LP neuron, basically. And what is convenient about this reference is that they basically provide us with a set of models that we can use. So here are basically 4 candidates that were found by a very brute force parameter sweep within this. Like if you read this publication, they basically do a massive 20 million parameter sweep, and they find a handful of parameter sets that work, basically. It's a very inefficient way of doing this, of solving this problem. I'm not saying it's the best way, but it's convenient because these models are completely black box, right? They're not even the result of some optimization function. They're not, I mean, they're basically parameter vectors, and we're just comparing the 2 parameter vectors. And some of them work, most of them don't. And in particular, you cannot interpolate. So if I go from this blue curve, if I take the parameters for this blue curve and this red curve, and I try to interpolate between the 2, I'm not going to get anything that looks like the data in the meantime. So that's kind of the key feature that I'm thinking about, is that you can't just kind of interpolate. So these are really discrete parameter sets that you're and you're trying to choose which ones are better. And by eye, you might say, well, you know, these blue and red curves, they look more like my data than the green and the yellow curves. And that's kind of what we are trying to get the criterion to say in a kind of more quantitative way, right?
Sorry, one thing.
Yes.
So these parameters, are these parameters for a fixed set of equations, or is the structure of the equation also one of the parameters?
That's the next point, right? So, and that's kind of one of the differences. So this is the classical setup on the left, where you would compare 2 sets of equations. And usually model selection criteria are set up in a way that you assume that you've maximized the parameters, and you're just comparing that model class versus the other model class, right? Generally, in the kind of applications I'm interested in, you don't only want to compare the model class, you actually want to compare that specific vector of parameters, which is what you have on the right. So yeah, classical statistics would basically do that thing on the left. And then what we want to do is do something that does both. That's able to do both. So it'll essentially, we're always comparing specific parameterizations with specific vectors. So I'm going to say model from now on, it's always going to be just model and parameters, not just a model like this.
How many parameters do you have?
And this one, like a dozen or so for each. I mean, the number, yeah, essentially, it's because you have 8 channels. Each channel has, actually, so it depends what you mean by a parameter. A lot of parameters are fitted experimentally, like the reversal potentials and the curves, like all the parameters for the curves M and H, they're kind of fitted by experiment. So if you count those, it's a lot more. If you only count what they were sweeping, which is I think 8 parameters, then it's only these maximum conductance scalars that you have here. So they're kind of the relative strength of each channel. And that's the only thing that you're kind of moving around. Everything else is fixed. It depends exactly how you want to formalize. But yeah, you're in the realm of like a dozen parameters or so. The number doesn't really matter, and it's not going to matter for what we're doing.
Then,
yeah.
Sorry, and when you choose the parameter, then some of them will change more or less the behavior around certain value of the parameter. If you have some sort of complexity close to the parameter set.
You mean like how sensitive is the model to the parameter?
How sensitive?
Yeah, this is very sensitive. These are non-stiff, like these are highly stiff equations. So basically because you have like relatively slow dynamics most of the time, but then these spikes are resolved, right? They're integrated. They're not like events that you put in, and they occur over like a millisecond or so, in which you don't really see at this resolution. So the equations are quite stiff, and yeah, so there's quite a bit of like sensitivity. Which is why it's hard to define. I mean, nowadays you can do gradient descent on something like this if you set it up correctly. I think in 2004 that would have been more difficult, but today you could probably do this. You can also do MCMC. I mean, the reason I know this is because I had colleagues that did Bayesian inversion for this. All right, right. So we have this. What we want to do is we have some kind of some collection of models that can be quite large, and then we want to come up with selection criteria that's going to prune this model down, this collection down to something small, right? You'll notice I don't necessarily have just one model. Because I think it's important that we keep the option that maybe some two models are not, one is not objectively or irrefutably better than the other. So this set is not necessarily going to be one, but we hopefully can reduce the amount. Basically, we want to remove what the evidence is enough to remove and keep the rest. And maybe then what that will mean is you can use this reduced set and say, well, look, I have these two models, I still can't distinguish. Here's an experiment, here's the kind of experiment I would need to go back and get the data that I need to make the difference between these two models. And so that can kind of guide that experimental loop as you keep kind of improving your design. And like I mentioned, from now on, I'm never going to write theta as a parameter, it's just subsumed into M, right? So my model is model and parameters, whatever that combination is. Okay, so yeah, we're not going to have a fourth choice, and we are going to basically use the expected loss as the way that we rank models. So like I was saying earlier, we assume that we have some functional Q that just gives us some loss. So whenever, for every prediction of the model, it returns a real number and it says you were wrong by this much, or this is how much it costs, this is how much your error cost you, and we want to minimize this. So it's minimization of the risk. Which is pretty much the standard practice for machine learning. I mean, I don't really know anyone in machine learning that doesn't do this. In statistics, it is a bit more varied what people use to fit, but from I think from an operational point of view, this is clearly like the better choice.
So the loss here is based on some like maximum likelihood?
It's whatever you want.
Whatever you want.
It's whatever your application requires. So you can, so basically, you know, if your application is insensitive to certain types of errors, you could decide to exclude those from your loss, if that makes sense to you. You know.
Yeah, I was wondering about the risk, because you take the expectation with respect to a true model.
Yes.
Which you don't know, of course. So.
Well, I mean, you have data, right? So you're assuming that you have some black box machine that can spit out data. They can spit out samples, right? So in this sense, you can very much approximate this by you just evaluate the loss on your sample.
So you take a type of non-parametric version of distribution.
I mean, it's the average over your data. You take the loss and you just average over.
Okay.
It's nothing more complicated than that.
Yeah.
And that's, I mean, that's kind of the key, right? So we don't have access to the true model, obviously, but we do have access to a data generating machine. And that's going to be the way that we kind of get information out of the true model. And with the one thing you can do with a data generating machine is compute expectations over the true model. You basically can't do anything else. So we have to massage whatever we want to do into something that comes out as expectation of the true model, and then everything else has to be in the model.
But you are now assuming still that your data generating machine does have some noise and maybe the data itself is not completely accurate.
Oh, it's measurement of the same conditions.
Yeah, okay. So these are very that is actually what we are going to account for. And what is one of the things that's missing from a lot of statistical criteria is the fact that, you know, if you change labs, your data generating machine is going to be slightly different, basically and unavoidably. And that's something that is maybe the most important point. So that's a very good thing to point out. But to go back to what you were saying, what was your question again? The
data is not perfect.
Yeah, the data is not perfect. Right. Okay. So the way I'm gonna formalize this is that if your data is not perfect, then that would somehow be your prediction. That's gonna come out as a prediction error. So if you want, the goal would be to have a model that perfectly represents the data, including the noise, by literally including the noise generating process in your model. So if you think that your recording is Gaussian, kind of it gets some Gaussian noise on top, then your model should include a Gaussian term that describes what the noise is, and therefore you know what that is. That's going to be the framework for that. I think it's just one way to do it. Yeah.
What about if the noise is somehow correlated to the conditions or the parameter space? So you see,
Right.
so it goes back to, I think,
Yeah.
your question. If you see some areas of the system which are highly, so will this affect the whole?
So, yeah, I mean, let's bank that question, and I think it'll be a bit easier to answer when I'm a few slides ahead. But it's a good question. All right. Right. So just to kind of summarize this, so we have basically this is just showing that you can have a variety of different amounts of confusion between your two models. So you go from a case where the two are essentially indistinguishable up to a case where it's very clear which one is better, right? So we have these kind of parameters that we can explore to see how this thing behaves. And the main thing I wanted to highlight here is that if you just take the risk, evaluate on these data points, that's not good enough because it only it has no notion of distance, right? So you don't know whether are these two lines close or far? I mean, there's no notion of distance in the risk space because if I add more data, these things are going to spread. The distance is proportional to the number of data points. That goes back to the thing that we don't want to have something that's sensitive to the number of data points. And you'll notice too that these two are actually flipped, like the order is flipped compared to the other ones. So that's also something that is a sign of a behavior that we don't want. Okay, what we actually want to have, yes.
Isn't the distance between your observations in some sense related to your number of data points? Like goes to sort of 1 over the square root of n, like
Then okay, yes.
More simple, yeah.
Right. So if you're assuming that your data generating process is completely predictable and reproducible, that you have, if I repeat the experiment tomorrow or in another group, then I will get to infinite accuracy the same data generating process, then this is true.
Yeah.
But if I don't, then you're going to underestimate the error if you do this.
Mm-hmm.
Because you can get arbitrary confidence by just recording more data.
Yeah.
And that's also something you get with significance tests. If you compute significance tests with with probabilities 10 to the minus 25, that's not a sign that okay, it's fairly certain, but mostly it's a sign that you're outside of the validity regime. You have so much data that these kind of tests don't really make sense anymore. So what we want is, rather than having single lines, we'd like to have distributions, right? So we would like to have not a single value of the risk, but some kind of idea of if I were, basically I don't really care about the risk for this data set. I care about what would be the risk, what is the distribution of values of the risk that I'm going to get if I were to reproduce the experiment, tomorrow in another lab with another mouse with whatever. Yeah.
What's the definition of this?
The expectation of the loss.
Okay.
Yeah. It's the average loss over your data. So
now there's expected risk.
yeah, I think it's the same. I think this is a typo.
But then what is the source of uncertainty? So it's distributions rather than.
This is what the talk's about. This is what we're going to talk about. How can I put distributions on this? Because at the moment, this is what we would like, but at the moment we don't know how to do this. Because other than repeating the experiment a bunch of different times in different conditions and kind of looking at what varies, even that you might still miss something if you do this. So this is what we want. But at the moment we don't know how to do this. Okay, so basically what is kind of our intuition here? Maybe I go back just to highlight these things. So what are we kind of observing is that in this case, I would say, that the two models are very difficult to distinguish in this case. Because there's so much noise and the curves are so close, it's hard to say, if you told me, oh, clearly the Planck model is better, I'd be like, maybe, but not based on these data. So there is a kind of relationship between the amount of noise and the certainty with which I'm going to select the model. Whereas, down here, it's maybe a bit hard to see, but even though the curves are close, the kind of the data are so precise and they're so precisely located on the blue curve that you could start to make an argument that the Planck model is better based on these data. And of course, you know, if you just choose a place where the thing is completely different, then that's clear. But this is kind of an this is less of a relevant case because in here you don't really need a model selection criterion anymore. You can just look at the data and that's enough. So we're kind of interested in making the difference between, you know, a situation like this, where the curves are close, but somehow still separated enough relative to the noise, and something like this where the noise kind of swamps out the difference. So that's the intuition. You can kind of see how this pans out over here. So here the two distributions, the risk, you know, very overlap quite a bit. And as you go down to this corner here, then you see some nice separation where, you know, one of them is more concentrated. So this is kind of our intuition, right? So we have, if you have more predictive accuracy, then you should get somehow a more reliable comparison. And the reason for this, or at least the way that I think this is, or at least the one way that I argue for this, is that if you know the source of variability, so this goes back to Val's question. If you know that there is this form of noise in your experiment, or you know that your experiment is sensitive to the temperature in the laboratory or the amount of vibration, then you can either put this in the model, right? So you can have a temperature parameter in your model that's going to be included, or you can design the experiment in such a way that you can control for these variables. So either you remove the noise by the experimental design, or you include in the model. Either case, it's something that you're aware of and that you can that will be accounted for in your predictions. And then what that means is that any discrepancies that are left, so if you have differences between your prediction and your data, then these should be somehow sources of variability that you did not account for. So there are things that you're not controlling for in the experiment, and there are things that you're not including in your mathematical model. So that's kind of going to be the key assumption that we're going to work with. So we're saying that any discrepancy between prediction and data is going to be the kind of thing that can vary when I replicate. Okay. All right. So just kind of recap what we're playing with. Like our starting situation is that we have a bunch of models that we want to compare. We're going to assume that each model is somehow probabilistic, so that it predicts, it's not a deterministic model, but it predicts probability distributions over data spaces. And the reason I need this is because I want to be able to generate synthetic data with my model. And if I generate single points, I'm not going to get distributions. So I need the generated data to be distributed somehow. We're going to assume that we have some loss function that goes from the data space to real numbers. I'm writing them as XY because often these are going to be like input-output data points, but they don't, theoretically this could just be X as well if it's like a static distribution, that would also work. But I think this is at least easier to latch on whatever your preferred model would look like. And we're also going to assume that we're able to sample from M true. So this is a comment earlier that we have this, we don't know the true model, but we have this kind of black box that can produce as much data as we need for our. So these are like the ingredients that we're assuming that we have. Now, these are all kind of things that I've already mentioned. So this is, the empirical risk is the sampling estimate of the true risk. So you just average over your data points. And then basically this goes back to like what I was showing before, right? So if you were to just evaluate the risk on the points, you would get lines like this for each of your models. And if you just take the lowest one, you're going to force a choice with no consideration for the uncertainty. And what we're going to go towards is replacing these by distributions. So that we can then, what we're going to say is that we're going to reject the model if the probability of its risk being lower than enough, like we're going to reject model B if the probability of its risk being lower than that of model A is less than 5%, or something like that. And you can do this directly from these curves. It's just tail probabilities from these curves. So you It's actually quite easy to compute. And that's maybe one of the key features here is that we actually get interpretable, testable probabilities out of this, which maybe goes back to your point a bit, that you can actually, at the end, you're going to get a probability of selecting one model over the other. And you could, in theory, go out and test whether this probability is correct because it's a testable problem. And I'm for sure not going to have time to talk about it, but that's one way that we use for calibrating the method in part of the steps.
And what is now the sort of certainty in these expected risks?
Right. So this is the
not distributions.
Yeah. So this is the uncertainty that we're going to bootstrap from the error, the prediction errors. So I basically have I have a discrepancy between what my model predicts and what I record from the data. And I'm going to use that to kind of induce a distribution on risks. So this is where we're going.
The noise comes from both the system and the model.
From the system and the model. No, only the noise here is purely a noise from the prediction errors. Like the fact that your model is stochastic will not, you could have a highly stochastic model and still get like precise risk prediction. Right? You can very accurately predict how wrong your model is. Right? This is really beyond that, is like how wrong is your prediction of the cost. All right, so the rest of the talk is going to be how do we measure this thing and how do we turn it into those things. All right, so now I'm going to go through the most pedestrian. So this is a very simple, from the mathematical point of view, this is going to be a very trivial derivation. But I think conceptually it's very useful to see kind of what we're doing. And it's kind of the key trick, or yeah, maybe one of the key things that make this method, I think, much more generalizable than other things. So we start from whoops, where are we now? Okay, there we go. So we start from what is it that we want to compute? We want to compute the expected risk, right? So that's the expectation of the loss. Again, with the true model, and that is you can just rewrite this as an integral over the data with the probability of each data point coming in through here, right? No issue there. Then what can I do? Well, I can just reorder the integral. Right? So I just pull out. So what I'm going to do essentially is I'm going to slice up the data space into slices where the loss is fixed. Right? So this amounts to just applying Fubini's theorem to like swap the order of the integral space. And just doing it in a particular way that allows me to factor out the Q as the outside factor. Now having done that, well, if you look at this thing here, yes.
The Q, is there some decision there about what constitutes constant? Or do you really mean absolute?
Absolute constant in this. I mean, at this point, this is formal. And then we're gonna, the next click is gonna turn this into something we can actually compute. But this is formal, like it's actually, exact Q. Whether the space is continuous or not, put Dirac or wherever you need for this thing to be valid. That's not a problem. Of course, if you then integrate over the entire data space, the probability of getting P and X and then evaluating Q, that's basically just probability of observing Q. And then you're left with just an integral over Q. All right. So as you mentioned, this would not be a very useful quantity because you have finite data, and even if you had infinite data, like an exact slice is not very useful. But what you can do is just replace this with a lesser equal sign. And then you work with cumulative distributions instead of densities. Generally speaking, cumulative distributions, big winners compared to densities is my experience. Because this you can just compute very easily from the data. Right, so I wrote it with an Iverson bracket. If you prefer heavy side functions, it's the same. You just put a minus in. So now we're almost done, right? Because if you get the probability, you can just rewrite this as a derivative of the cumulative density. All right. And then you say that the dq cancels the dq. If you're if you're a mathematician, you apply the fundamental theorem of calculus, whichever way you prefer, you come up with this. Right? So yeah, and then we're pretty much done, right? Because now we went from something that was an expectation over the entire data space, which would be like a nightmare to compute. And it's very high dimensional. Like the bigger you take your data space, the more mainly when we've boiled it down to a one-dimensional integral, but a one-dimensional integral with fixed bounds. Like it always goes from 0 to 1. So this is really, really nice because then everything that we need to do now can be reduced to one-dimensional problem, no matter what the starting model was. And just to kind of give you an idea what these things look like, so we have a few examples of distributions of the loss on the left. So these are CDFs. And then what we're actually playing around here is the quantile functions. So the reciprocal, or rather the inverse of those CDFs. So these are, PPF is the point process function, or the quantile function, whichever you prefer. I use PPF because it's an abbreviation, it's shorter, but it's like you prefer. It's basically just you flip the axes. Literally, the way you do this is you compute the empirical CDF. So you take all the data that you record, you just evaluate the loss on all of them, you sort the loss, and then that gives you a CDF. And then if you want the quantile function, you go with your array in NumPy and you just swap the order of the axes. That's all you need to do. So computationally, this is super easy. It's very, very convenient for the computations. Because when you're working with samples, it's very tractable to translate this into quantities over samples, which is good because you remember the only thing we have is samples from the true model. We can't actually take integrals. Okay, I think what is there left? Oh yeah, okay, that's the thing. Yeah, we can't actually compute this. Just to remind you, what we're actually going to be doing is computing averages. So this whole thing comes down to literally just computing the averages, which makes sense, right? Because we started with this. So it kind of has to be equal to that. But it'll be useful to know that we can relate it to a one-dimensional integral. That's what we're going to base the theory on. Maybe just a minor point. I find it easier to think about what we're going to do next as integrating over the functions, these quantile functions. That's not quite correct because the quantile function is the measure of the integral. So, but conceptually, you can I think it's easier to not have to always convert in your head that you're working with measures instead of the function. So you can just think that we're integrating this. Just keep in mind that, technically it's slightly different, but from now on, we're only going to think about the thing that we need to describe is, I think, yeah, that's the next point. Okay. So this is the key point from this is that if we want to, for the purposes of computing risk, the only thing we need is this function, this quantile function. Right? We haven't done any approximation, we've just reordered integral. And therefore, the rest of the theory is going to be, how do I describe my uncertainty on these curves? And so the trick is going to be, how do I put a stochastic process on quantile functions?
Maybe.
Yeah.
Another way to say you need to estimate blue curve, and you want to have some sort of
yeah. So
error on the estimate on the blue curve.
Yeah, or it's not even the error of the estimate. You want to know across replications, how much is this blue curve going to change? That's maybe the better way to frame the question. So we're trying to get, and what we're going to do is, we're going to look at the discrepancy between the two things to do this. So basically, if you do, what you can do is you can repeat the whole thing that we just did, rather than using the true model to generate your data points. You can just use the model itself. Right? So this is why I need a probabilistic model, because like I said, I want to be able to generate data from my model. And if I do that, then I get a kind of self-consistency condition, if you want, that should my model be perfectly true, should my MA be equal to M true, then these two would be completely equivalent, right? And so any difference between those two curves is going to be due to some errors in the model. Not all errors are going to cause discrepancies, but all discrepancies are due to errors in the model. And so what I end up with is a kind of, I can draw the two curves in this space, and the difference between the two is what I'm going to call my delta. And that's my discrepancy. And I call this EMD because, like I mentioned earlier, I'm computing these from empirical data, and it's the discrepancy of the model, so empirical modeling discrepancy. I don't know if I use these, but anyway, the way I name these two quantities is, this guy is the mixed, is going to be our mixed quantile function, because I'm mixing both the true model and the model, or the true data generating process and the model, and this is going to be my synthetic quantities because there's no real data. Okay. All right. So this is, I think, enough with the conceptual part. So just to kind of take a breath and see what all these things are going to be slotted into and what we have left to do. So we assume that a priori, someone has given us a collection of models, right? So this could be by fitting, this could be by, parameter search, whatever, what have you. This is kind of done somehow a priori. It's not something we're worried about. We assume that we're given these models. Now, what we do is we take the observed data and we compare it with the models, and then from that we get two quantile functions. And the difference between those is going to somehow quantify how wrong our predictions are. Then what we're left, what the rest of the talk is going to kind of go over, is that we're using this difference, we're going to generate a stochastic process over these quantile functions. There's a parameter C that shows up here, which we're not going to have time to talk about, but I'm happy to talk about afterwards. And then from that, we're going to sample a bunch of different we're going to sample a bunch of these different quantile functions. So we get because we get a stochastic process over this, we can just sample the stochastic process. Each of them provides a quantile function, a different one, that we, of course, somehow wanted to encapsulate both the shape of this curve and also the spread between them. So the more the difference, the more these guys should vary. And each of these curves, as you recall, we can just integrate it to get the risk. And so if we do this for each curve and we just kind of histogram the resulting thing, then this answers everyone's question. This is how we get distributions on those. So we've somehow induced a distribution of the risk by sampling the underlying quantile function. And then, of course, we repeat this with all the models, and that's how we get a collection of different models. All right. So, like I said, I won't have time to talk about how this C is selected, but what I do want to spend a bit of time talking about is how do you define a quantile process over quantile functions, because that's a highly non-trivial thing, and your usual toolkit doesn't work for this, and that's what I want to explain. Any questions on this though for now before we continue on? Yes.
So the variation in these distributions, in these RA distributions,
Yeah.
they do not come from uncertainty in the model. They come from the uncertainty you introduce yourself in this.
Yeah, they come from the modeling errors.
So you have this function Q that,
Yeah.
But this is something that you introduce yourself.
Yes.
Toxicity.
Yeah, it's going to be parameterized by this delta, and that delta is capturing the prediction error. Because the delta is 0. So basically, if you have 0 prediction error, that delta is always going to be 0.
Mm-hmm.
And so if the delta is not 0, it means you have some prediction error. And not only that, but that prediction error is very directly related to how wrong you're going to be in the calculation of the loss. because it's prediction error on these quantile functions, which are what you need to compute the loss. Yes.
Earlier you said that you can also have that not all wrong predictions necessarily give you a distance in
Yeah.
your delta.
Yeah.
How do you, if you use this, do you later check if there are other things that could have gone wrong, or?
I mean, not in this framework, but I would say that anyone that fits models with with a scalar objective would have the same issue. This is like, I think completely, it's a general issue that applies to any kind of fitting with a scalar objective, right? Because you have an n-dimensional model projected down to a one-dimensional loss space, it cannot be a bijective map. It has to be surjective. Okay. All right. Where are we at? Oh yeah. So we are here. So what is it that we want, right? So we want now the last point that I want to talk about is like, how do you define the stochastic process? On the left, you kind of have the ingredients that we've already presented. What is it that we need, right? So one thing you'll notice is that these curves on the left, they're always monotone, right? They have to be monotone increasing, because otherwise it's not a CDF, right? This is actually something that I unfortunately had to learn by mistake, and saying like, maybe it's not so important, maybe I can get away with something that's not. No, you really, otherwise the distributions are complete garbage. So that's one, but I mean, that's not so hard to do, right? The monotone process exists. You can take a Wiener process, threshold it, and you get something that's kind of monotone. The other thing that you want is that the thing is integrable. That seems to be pretty. We're going to compute the risk by integrating the function. So if the integral doesn't exist or diverges, kind of a problem. If you're familiar with like white noise processes, this is where the square root delta t comes from, like the integrability condition. One kind of somewhat sloppy way to write it is that, if you look at the expectation between the difference between 2 points along these curves, so you remember that phi here is going to be the x-axis on these curves, right? Because we're using phi as a measure. And you basically want that the difference here is somehow at least sublinear in delta phi. That's one way to write integrability in a kind of concise enough way that I can fit on the slides. I mean, there are other ways you can do this. But again, it's an important thing, but I kind of don't want to focus on it too much. I think more interesting is this non-accumulating property. Because that's less trivial, and it kind of took me more time to figure out that this was important, because I was doing things with Wiener processes and it wasn't working. And then I was trying to figure out why, and I came up with like, this is the key feature. And it's like, what does this mean? It's like, if you think about how these curves are generated, right? So I have my model that's spitting out, data points, and for every data point, I compute the loss, and I put it somewhere on this curve, right? I'm not starting from the left and accumulating points to the right in general. Right? It's effective if you, from the point of view of the CDF curve, the whole thing is completely shuffled. Like the data points come in arbitrary order. So if you have something like a Wiener process where the variance somehow depends on the distance from the initial point, this is completely wrong. That's going to give you completely the wrong distributions, because there is no notion of direction in these CDF curves. So you somehow have to sample the entire interval simultaneously. It's not like you can't do something like this where you start from one end and you keep adding noise to go to the other end, because that's going to necessarily increase the variance as you go forward. Right, so this is kind of the point, right? So we must, whatever we do, we need something where the variance does not depend on phi, it only depends on the delta of phi. And that's going to be kind of the key thing that we need to think about. There are two other kind of fairly obvious things that we want, because we want these distributions to somehow be representative of the distribution of quantile functions. So if Q star is the distribution, is the quantile function for the real data, we want our distribution to somehow be centered around Q star in some sense of centered, which I will get to. And the same thing is that we want the variability of these functions to also be somehow proportional to delta Q. Again, notion of variability here is a bit ill-defined because I have to get there a bit. All right, so what do we do with this? So this is what we don't want to do, right? So we don't want to add noise progressively. What are we going to do instead? Like I said, the idea is you would like to do this kind of all at once. You kind of like simultaneously sample the entire interval, which might be possible, but it was slightly easier to do the math by taking a shortcut. Instead of doing it all at once, what I'm going to do is I'm going to successively refine the interval. So I start by picking 2 points, like the 2 endpoints. And then at every step, I have my interval. So I go from here, you know, my jumps are 1. So I have like delta 2 to the 0 is 1, right? So it's the entire thing. And this is also where you see it's convenient that my integrals go from a fixed 0 to 1, because I can write everything as that domain. And then at every step, I'm going to split this into 2 so that I now only sample the middle point here. And I do it in such a way that it's constrained to be bounded between these 2 endpoints. So this, like the gray bar here, represents the domain of the sample, of the point that I'm sampling. And then those conditions of being centered and having the correct variance are going to give me what that distribution actually looks like somewhere on that domain. Yeah, basically that's the idea. And then you repeat this, right? So you do this multiple times, and at every refinement step, you double the number of points that you get. And if you do this 8 times, you get about 1,000 points, or 500 points or something like this. It already gets fairly close to these curves. So if you need to do this about 8-10 times to get typically good enough curves for evaluating stuff. So that's the idea. And you can see that this is going to be, all right, well, maybe I should just point it out. Strictly speaking, right, we're not drawing these individual points. We're actually drawing the interval, the 2 increments that are constrained to be equal to whatever the difference between these 2 are. It's just a more productive way of thinking about it. I mean, you can think about, I draw 1 point between 2 bounds, or you can think I draw how far it is from left end and how far it is from the right end. Those are 2 equivalent ways, but the latter is somehow the more correct way to do this. And it's going to give you the more correct math, basically. So just think of this not as drawing each individual point, but every time drawing the lower interval and the higher interval with the constraint that they sum to 1. Right. So, and the reason this is the more correct math is because then you realize that you're actually needing to draw from a compositional distribution. And there is this very beautiful paper on, you know, the theory of compositional distributions that does, yeah, it was one of my most pleasant reads of a few years ago. You get like very out of the standard curriculum examples of like linear algebra on, you know, exponentially transforming spaces and all these things. So it's actually a really cool thing. What matters for us is that they will tell us that what you actually should be computing, like the most natural statistics for a compositional distribution, are not the expectation of the mean, not the expectation of the variance. Basically, because if you're close to the edge, right, so you can imagine over here, if I want to have something that's high variance, then it should somehow be asymmetric, right? Because if you had just a symmetric high variance distribution, it would go outside the bounds. And if you use just expectation and mean, there's no way to encode something that's high variance and still within bounds when you're approaching the edge. Whereas when you use the transforms of the compositional distribution, you can do this. And basically what you do, you take a logistic transform to map the interval to the unbounded space, and then you do a usual expectation variance in that space. It's not really more complicated. But it turns out to like actually work really well. And you may know already that the simplest compositional distribution that you'll find is a beta distribution. So normally the beta distribution is written like this, but you can just rewrite it like that. It's the same thing. But now you have your interval on the left and the right. And you have 2 parameters here you can control. And the controlling of these 2 parameters is what's going to give us a shape that we want. Okay, so if we go back to the desiderata that we wanted, we want something that's monotone, integrable, and non-accumulating. All these things are kind of by construction. So just the way, by doing this refinement process, we just guarantee that these are satisfied. We don't have to worry about them anymore. And now we have still two free parameters here, the alpha and the beta, and we have two criteria that we want to satisfy. So what's left now is just to set up some algebraic equations that will allow us to get this. Right, so like I said, centered in variability and compositional distributions, the most natural way to express those are what are called like slightly different definitions for this. Yeah, basically, this is what I was saying earlier. So for compositional distributions, you don't necessarily want to do the expectation, again, because of these bounds, and your distributions are going to become somehow squished when you get to the edges. So you do these logistic transforms. And if you work out the math, if you just the standard logistic transform, where you take everything as like logarithms, more or less, but it's like, yeah, logarithms on both ends, if you will. You basically get exponentials as your quantities. These are d gamma functions and tri gamma functions. For our purposes, it's not really important. It's just the point is these equations exist. You can pull them out of papers. All the theory is nice and clean. And so you can just apply this. So we have we have a quantity that gives us a variance. We have a quantity that gives us the mean, and we can use this to define distributions that are going to track the quantile function that we want. So that gives us two sets of equations, which we can then solve for alpha and beta. And the equations are here. So that's kind of the ratio of the step and the amount of variance. And now this C parameter here is going to be kind of what controls the conversion from our discrepancy that we measure in the quantile space to an amount of variability on the quantile process. So it's kind of a unit conversion factor if you want to define this. Okay. Yeah, this is just kind of another plot that kind of puts everything together, but in the interest of time, I think I'm gonna keep going. No, oh wait, I'm done. Wait. I had one more that I wanted to, oh, maybe it's same. Okay, cool, all right. I guess that's it. Well, not it, but I thought I had another slide that okay, I'm gonna skip this, right? So this is, the point of this slide is just to like compare to other criteria. Again, if you're interested, we can talk about offline, but move on, especially if you're familiar with these criteria, this will make more sense to you. But I had to satisfy the reviewers, I have to do this comparison. So basically, yeah, the main takeaway is that what we are doing is really qualitatively different in its behavior than all the other criteria in terms of the number of the data set size. Okay, yeah, this is the slide I thought I had put before the other one. Right, so I mentioned that this C here is basically how we convert discrepancies in the quantile space to variances. And essentially this is where kind of your domain knowledge is going to come in, because a priori, there is no theory that will tell you what this C should be. I mean, in a sense, it's already an assumption that this is proportional. That we just kind of put that in because it's the simplest assumption we can make. But this is something that you would have to do by some kind of experiment. Like you basically test by simulating variations of the setup, see how much what would be like a good value of C, and then from there you can kind of extract it. So I do have, did include some procedure for how you might want to do this. Yeah, I won't necessarily like go through it in detail, but just so you know that kind of this was something that I did look into how you might do that. And then that gives you at least a principled way of selecting this parameter here. It's not just something that you pull out of hat and hope that it works. So basically what you end up doing is you compare what the predictions of this theory would tell you with what some kind of ground truth accuracy would, like tail probabilities would be. So if you remember, the things that we're computing are real probabilities, right? They're the actual probability that one risk is lower than the other. That's the end, that's the kind of the end result is an actual probability, which means that we can then test it. And so the way you do this, or at least the way that I propose to do this, is you think about your setup, you're like, well, I think this setup is sensitive to these kind of variations. So I'm going to assume that I have a certain type of variation and run thousands of simulated experiments, see how many of them select one way, how many of them select the other way, and see if that matches with what I have. And what you can then draw are like these kind of diagrams where the white part is the region where my criterion is more conservative than reality. So where I'm underestimating the confidence. And that's basically where I want to be, right? What I want to avoid is having an overconfident criterion. If I'm underconfident, it basically means I'm gonna like not make full use of my data, but at least I'm not gonna reject models that I should have kept. That's the basic idea. Okay, all right. And so we're already at the end. Good, because I'm already out of time. So if you remember, like this is what we started from. This is like our setup, what we wanted to do. We said that we wanted to use the risk to rank the models. This is kind of our working setup. We made this realization that if you want to compute the risk, the only thing you need is a one-dimensional integral of the quantile function. Then we use this to kind of motivate the assumption that any discrepancy in these quantile functions are going to be related to things that are either not controlling the experiment or not being accurately modeled in the model. And therefore, things that might change when I replicate, because I'm somehow unaware of that source of variability. Or I don't know how to control for it, or I'm not able to control for it. And so from that, then we made an ansatz that we assumed that the model uncertainty, or like this metric variance, is proportional to the discrepancy between these two curves. And then from that, then we defined a hierarchical beta process, which is this thing that I constructed in order to satisfy all these criteria, right? That it be monotone, that it be non-accumulating, and that it somehow track in some sensible way the actual quantile functions that I have. And at the end, we get distribution like this, which we can use to compare. And this is just a reminder. I mean, this is a figure you've already seen. Just the other one was the key ideas. This is the summary of the procedure, how the thing works. And with that, I would thank you for your attention. So yeah, again, this is where we are. This is me. This is the professor I'm working with. And if you're interested in higher order networks, we started last year having a workshop. So we should have one again next year. So if you're interested in especially like dynamics on higher order networks, or learning of networks, this is something that we're running. So if you're interested, just kind of get in touch and we can let you know when that happens. And yeah, otherwise I would thank you again for your attention, and that's all I have to say.
Do you have any
I'm just wondering why, so I didn't define the stochastic process, and I'm not sure why. I mean, is this more efficient than just bootstrap over your actual data and generated data from the model?
It's different. It'll give you different
It
distribution.
give different answers.
Yeah.
This I understand, but would it be like, why would it be more useful, let's say? In which
So the bootstrap is not going to account for replication variation, basically. So if you have very large data sets, the bootstrap is going to give you direct delta distribution.
That you're getting data from multiple, okay, so you're simulating some sort of variability on the true model.
Right. So the point, okay, so I mean, if you're interested in modeling how my loss is going to vary across experiments, and you can somehow convince 200 people to do the same experiment and each give you a result, and you could use that to get a distribution, but that is unlikely to happen.
Yeah.
So the idea here is that you only have this data set, and you're trying to, at least from the data that I have, can I get some sense of how this would vary across experiments?
But you have to have some ideas on how this is gonna vary.
Right, right. So that, I mean, that's the calibration procedure that I kind of skipped over, and where it's going to be important to not. It's important to kind of consider what do people know about these systems, and you can't just do this if you're pure like statistically inclined or just pure modeling. You then have to go and talk with the people doing the experiment and ask like, okay, like when you do your setup, how does it change across things? And I mean, they know a ton. They know a ton of stuff. And then you can include, the idea is that rather than ask 200 people to repeat the experiment, you can ask them, what do you think matters? Like, what are you already controlling for? And then you can do not 200, but 10,000 simulated experiments in your computer, get much better statistics. And in that way, get a handle on how these things vary. And at least for the known parameters of known distributions. And then the hope is that if you've covered enough bases with the things that you know about, then that should, not be completely off the things that you're not accounting. Because at the end, I mean, this discrepancy function doesn't, like, it's agnostic to where the discrepancy comes from. So we will consider things that you might never have considered, but still that scaling factor C should not be completely wrong. Maybe I should, the last point on that, like each of these, so what you end up doing is they end up defining things that I call epistemic distributions. So epistemic because it's like the actual data generating process changes. So you're basically simulating different labs. And you might say, well, I think, across labs, the sensitivity of the device is somewhere between 1 and 1.5. And so I'm going to put a uniform distribution on 1 to 1.5, and that's going to give me one of these panels. Right? And then you say, well, okay, maybe it's 1 to 1.5, but maybe also it goes up to 2. I'm not really sure. And so you could do another panel where you have it go up to 2. And then you choose a C value that somehow works for all of these. So that's also the difference. You're not really defining a prior over these models. So a prior would kind of constrain you or like wed you to one of these. You can be more robust. So you can, even if you don't know exactly how the things vary, or maybe in one case they vary one way, in another case they vary another way, you can account for this by just taking a kind of minimum or maximum C. Essentially, the bigger the C, the less powerful you make the criterion. So the bigger the C, the broader the distributions are going to be, and therefore the more data you're going to need. But it also means that you're more conservative in your choices. So in case of doubt, you can always make C a bit bigger somehow. I mean, somehow in my experiments with the two models that I had, even though the regimes are very different, values around it, I always ended up that good values were like 1/2, 1/4. But that might be, I mean, I only have 2 types of data sets. I mean, I wouldn't be willing to claim that these are universal values. Yeah.
So what you're explaining is that you need some sort of, after you did your fitting procedure, you need to do the estimates from the distribution, you need some extra outside information from the experimentalist to make it work. But couldn't you just have used this outside information that you have already just in your first estimate instead? Like use sort of variation prior and then
not really. Or even really not. The reason for that is because it's kind of hidden in like how I compute these things on the left, right? So what you have is you have data, you're given some data, right? And you're trying to decide how decisive are these data, right? That's at the end what you're trying to do. The way that I get the true distributions here is like these are only defined over distribution over multiple realizations of the experiment. They're not you cannot use this procedure to assign an uncertainty to a particular data set. They're only valid as distributions of data sets. Basically because every time you do one of these experiments, the true value is either one or the other. Right? It's always a binary choice. Like on the left end, you're essentially trying to correlate. So basically what you're doing here is you're correlating a continuous variable, which is the probability that you get from the theory, with a binary choice, which is what, if you actually simulate this, and what you're doing is you're saying, I ran my experiment, I computed the risk for both models, A was smaller than B. I ran another experiment, I computed the risk for the models, oh, B was smaller than A this time. And then you do this multiple times. But each time you just get, A or B. It's a binary variable. So the original data you get from this is basically just a bunch of points down here and a bunch of points up here. It's just 0 or 1. And then what I do is you histogram over some small value, and you look at how many within a slice of this, how many of the model, how many times did I choose for A and how many times did I choose for B. Right? And then from there you can get something that should correlate with the theory, but that is not assigned to any particular data set anymore. So that's the conceptual reason why it's really a different quality, and you will not be able to do this on a single point. The other very valid reason, I would say, is that these computations take, like, I don't know, 45 seconds, and these might take a few hours. Because you have to simulate the experiment like whatever many times. And you also have to think about all the different ways things could go wrong. Because at the end you've distilled all of that down to a single scalar. That's, generally speaking, when you reduce dimensionality, you make things more robust. You are less sensitive to whatever modeling errors you made, right? So if you're able to reduce all of that uncertainty, like all of variability across models, all that domain knowledge to a single scalar, that means you can make a lot of mistakes. And that scalar should still be in the right domain, in the right regime. And so in that sense, I would expect that this is somehow more robust to modeling errors, where this might be more sensitive because you have to get them really right in some comparison. Yeah.
I was wondering if I could interpret your C as something to do with the invariance across the different contexts in which you could instantiate these experiments. I'm thinking of contextual bandits, sort of that invariant properties.
You get them as invariance across the replicates, is what you say. Maybe in some kind of ideal case. I don't think the connection is so direct.
Absolutely.
Yeah. I think it's more a case like if like something that's invariant across replications would be a kind of ideal case, because then you would expect things to be preserved, and therefore representing them as a single scalar factor might work quite well. Whereas if things change a lot between replications, maybe at some point, just scaling the whole thing up by some factor might start to be not work so well. All of this is kind of assuming that your models don't suck. Right. So you can kind of think of all of this as like, I'm assuming that my models are somehow close to optimal, or they're doing a pretty good job, and therefore, first order approximations are all kind of a decent way. If the things are completely off the chart, then a lot of these distributions, if I give these, if I compare the better models and the worst models, the one that you can just by eye see that, D is much worse than A, I think. You have them here, actually. So you see D is a much worse model than A. You can see this just by looking at the plots. And you see that also the correlation is not so great. Because the theory starts to break down as you get the model more wrong. But also, I kind of don't care, because if the model is so bad that I can see it by eye, then I don't really need this.
Okay, there's no more questions. Let's thank the speaker.